Okay, so this is the first explainer that we've got, and we're going to take a really quite high level view about machine learning, aka ML. So if I use ML, that's what I'm talking about. It's going to be about the why do we do machine learning, what is machine learning, and then obviously in the rest of the course a lot about how we do machine learning. But so we'll just cover some high level principles about sort of the steps and processes that we do, which we can get into more detail throughout the course. So great idea is a lot of this should be pretty high level, not a lot of maths or no maths in this section. So really lots of take home, but I really want you to understand or take home really clear ideas of where machine learning can add value, really clear ideas of what machine learning is, what it's not, and I think that's a really important thing. It's not a tool for everything, but it's extremely effective at certain tasks, and understanding where they can add value and how they can add value is really essential to sort of starting your journey in machine learning. So really excited. So let's do it. So I guess the question, why machine learning? And there's lots of reasons why machine learning, and it's almost like a perfect storm. And I would see it as two really fundamental things coming together at the same time. Like, why didn't we really do proper machine learning 100 years ago? And the reason for that really is twofold. It's around the explosion of data we now collect, and that really has been liberated by technology, about hardware, around computers. Not only the ability to do computations, which are a core part of machine learning, but also the ability to collect data, the ability to communicate by sensors, by devices like mobile phones, etc. This has seen an unprecedented amount of data being collected, a data explosion. So yeah, some facts which actually I didn't know to the level of this. Data has increased by 50-fold between 2010 and 2020. Amazing, but not surprising. In the digiLab office, when I was writing these slides, I was saying, well, how much data do you think we've got globally in 2020? And it's a bit like that question of how many sweets are in the cookie jar. You have no real idea of what this means. Apparently the answer is there are 44 zettabytes, and a zettabyte is 44 trillion gigabytes. I mean, this is just astronomical amounts of data. So yeah, to underpin what has really driven this is really that increased capacity and cheap storage of data. It's about modern computing devices. I mean, I've got a very powerful computer and it's just sat on my desk. We've got access to computers in the cloud which are extremely expensive, or national computers which can do extremely huge computations. This ability to compute is central to machine learning. And then we've got devices. Lots of companies, startups that I see are generating new devices to measure new types of data. But what do they do with that data? They need to process it and gain insight from it. And this really drives the need for machine learning. So yeah, that fundamental question, how do we extract value from this impressive amount of data? And I'm going to try and convince you that machine learning is one of those answers. And I don't think it's going to be very hard, right? So today, can you think of something that you use every day or once a week or once a year that is actually fundamentally uses machine learning under the hood? And actually, I can think of lots, and I've written a few down now, which I use in kind of my daily life. Maybe not the last one, the self-driving car, but hopefully in the future maybe. So obvious one, Google. I mean, an incredible algorithm that allows us to traverse the internet. It gives us access to information very fast, that's relevant, and now specialised to how we would like to see information based on our choices of picking. Incredible algorithm. We use it all the day without really knowing that is machine learning and AI under the hood. Recommender systems. So when you're sat there in the evening waiting wanting to watch a film, the under the hood is a machine learning algorithm that does the recommendation of what film you should watch or what films you might like. This was actually a fundamental machine learning challenge that was put to the community in the early 2000s by Netflix. It's called the Netflix Prize. And we'll talk about that in one of the other lectures. But yeah, it's actually a really interesting machine learning challenge, how you do recommendations based on other people's or similar types of users to yourself. Speech understanding, Alexa, you can ask, luckily I haven't got Alexa here, I've gone off. Yeah, you can all sorts of questions. You can have joke of the day to what's the weather to all sorts of things. Really clever bit of technology. Face recognition, widely used on phones now. Probably the latest one that everyone's talking about is ChatGPT, but in general, these large language models, I see them very much as, Google, contextualized Google. So, huge amounts of information can be efficiently extracted from lots of data and information that's stored. This is going to transform the way we do tasks, even in machine learning. But really clever technology, and I guess probably not widely used, but certain car manufacturers are getting there. Is around self-driving cars. Incredible technology, potentially safer, but some fundamental issues about how we deploy it. So really exciting technologies, really at the forefront of what we do, but some that we've been using for years. I mean, I guess this is from a personal point of view as well. I think we look heavily at the kind of branded, consumer-facing machine learning quite a lot. We're very used to Amazon's recommender systems, Netflix, using Google. But I think from my perspective as originating as a scientist, I think I see transformative benefits of machine learning in engineering and science. Part of digiLab's mission is how do we use machine learning to build a more sustainable world. I'm particularly focused on energy. But I've got a picture of some projects that we do, some projects that others do. So top left is can you find out where all the solar capacity is in the city using deep learning? That's a digiLab project. One of the actual transformative things in medicine is around diagnosis, using machine learning algorithms to recognize conditions like cancer, brain tumors, other complicated conditions. Is highly effective and a really good use of machine learning in my view. Intelligent farming, sensor systems around IoT, Internet of Things. You can monitor, you can optimize the growth of agricultural crops. Wind farms, something that we strongly look at. How do we optimize the location, the predictive maintenance of them, all machine learning problems. Bottom left, really fun challenge that we're looking at digiLab is around fusion. There's not actually a physical asset at the moment which can do full-scale fusion, and so a lot of it's done with simulation, so they can start thinking about what a fusion power station might look like when you scale it up and make those early design decisions. These are extremely expensive simulations, and at the heart of this, you can use machine learning to accelerate that process. Which can give insights rapidly so we can do more in that design space. And then the final one I showed is an example from DeepMind actually around folding of proteins, a project they called AlphaFold, but you can essentially design new proteins, which opens up a whole different areas of science and new possibilities in medicine, which is really exciting that machine learning can liberate that kind of activity. So what is machine learning? Like under the hood, what is it? I would say that it's, and I don't think there's one definition, but I personally see it as a set of algorithms and workflows which try and seek to learn from data. For me, the concept of intelligence comes from the fact that a machine learning algorithm can perform well on tasks it previously haven't seen. So it's this idea that it can learn from experience and then it can learn from that experience but then act intelligently or give a good answer on something that it hasn't directly seen. This transfer of knowledge, this generalization is the core concept of intelligence in machine learning algorithms for me. So I'll talk a lot about generalization. How we test to see if our algorithms generalize well is a really important part of validating if our models are good or not. And you'll hear me say it a lot. So machine learning comes in, it's not just one algorithm. I think that's a really important thing. And it's not one algorithm because machine learning algorithms often are joined together, so you can do multiple in one workflow. So I like to think of this concept of a pipeline of activities that you do to get from data to insight, but also it depends on the task which you're asked to do. different tasks need different algorithms to be designed to do different kind of outcomes that you might be interested in. So I'm going to talk briefly about 3 here, and you'll learn that this example in particular is a favourite of mine. So supervised learning is when we learn to perform a task by examples. So what we will typically get, the algorithm would like to classify a picture as either a cat or a dog. I use this example a lot. And so what we do in this algorithm is we have labeled data. So we have lots of pictures of animals, and then associated with those pictures, we have cat, cat, dog, the right label associated with it. And then the task of the machine learning algorithm is to be shown a picture of a dog or a cat, and that it hasn't seen before, and make sure that it classifies that animal in the right way. And this is a really interesting idea. There's lots of different algorithms that can do this. Neural networks, nearest neighbor can do this kind of classification. Gaussian processors can even do this process. You'll learn about all of those throughout these courses. But the fundamental task that you're looking at is I have labeled data. So I have examples of inputs that I'm interested in and the associated output. And then I'm going to try and build a machine learning model which reconstructs that same process and can generalize to unseen inputs. Okay, so opposed to supervised learning, there's something called unsupervised learning. And this is where you just have data. So you don't have labels associated with the output that you're trying to predict. And in unsupervised learning, there are different types. There's about dimension reduction, which is about simplifying data, or there's also clustering, which is what this picture represents. So really, I would say central to unsupervised learning, the idea is you're trying to seek to learn structure or patterns in your data so you can simplify it, generalize it, or inform how you build good models. So often unsupervised learning algorithms or tasks are used in the data preparation stage and the feature representation stage prior to a supervised learning algorithm. So these aren't if, either, or, they're often used together. And then one of my favorites, an area that I currently do research in as well, and an area that we actively work in digiLab, is around control. So reinforcement learning is really what we'd say is a machine learning algorithm that learns from experience. So what you do is you have certain ways to act in an environment or in a system, and then you reward good behavior if you're the outcome of your what we call your policy, the way you act in that environment leads to good outcomes. I always see it as very much how you train a dog, right? So your dog behaves well, you give it a cookie, or a dog biscuit, probably not a cookie. If it doesn't behave well, you tell it off. And it gradually learns or associates good behavior or the right behavior with the reward, and hope you reinforce that behavior. This is a really nice example, I think from a paper from Berkeley. So these are creatures, they're kind of somewhat like two-legged giraffe-like creatures. What the algorithm is seeking to learn is you will see all the muscles in this body. So this algorithm is going to get this two-legged giraffe to walk. Its reward is to stay upright as long as possible. And what the algorithm's got to learn is basically how it moves its muscles together so that it can stabilize itself and stay alive. What you'll see when I run the video is from, let me run it now. What you see is the iterations. So gradually this algorithm is learning how to optimally control the two-legged giraffe so it stays awake. Stays upright. So you see at 99 iterations fails, 216 it does kind of better but still doesn't last. And then by the 900th iteration, it's learnt from experience that the way to control the algorithm is known and it can achieve its goal of being able to stabilize itself. A really nice visual example of machine learning, particularly reinforcement learning. So fundamentally, machine learning is not a single method. What influences the machine learning method we choose? I think one of the fundamental questions you have to ask yourself is, how good do I need good to be? And I think that's really specific to the particular application. If I'm doing something safety critical, if I'm controlling aircraft, for example, I need to really accurate certain algorithm that I can trust. If I'm recommending whether you buy, I don't know, my classic example I'll use later, pink pants on Amazon, for example, if I don't choose to buy pink pants, then it doesn't really matter. So I think the fundamental choices, the methods we use needs to be related to the output we use, like how are we going to use that result, also what data we have available, what the task is. There are lots of considerations about how we construct these methods together, often multiple algorithms together, to go from that initial data all the way to some decision or some enabling insight into that data. So I think when we're thinking about what methods to use, we should think about what the application is, and we should also think about what kind of data we have, and that will really drive us one way or another, or make early decisions about what are the sort of algorithms we use. We won't talk about the algorithms, we'll just talk about the differences in data. So I think there's been a big push recently, and that's because of the big corporates like Amazon, Google collecting huge amounts of data. When you've got huge amounts of data which can be cheaply collected, then you can you can choose around building data-driven models. You have loads of data, you can use highly parameterized models, really complicated things like neural networks with lots of parameters in them. But if you think at the other end of the spectrum, something like a fusion reactor, well, we don't actually have lots of data about a fusion reactor, real world data. We haven't actually built a full-scale fusion reactor, but we do have mathematical simulations. But these mathematical simulations may take weeks to run on a supercomputer, and so we can't collect huge amounts of information about different possible runs of that fusion reactor. And so in that case, we have very limited but extremely rich data from a simulation. And this should drive the sort of algorithms that we choose and use. In the case for the simulation, we need methods that are robust to limited data. On the other hand, for big data, we need methods that can generalize and be very efficient over large data sets. So we need to think about these two extremes. Obviously, most problems sit somewhere between Amazon and Fusion Reactor in terms of the amounts of available data. One thing we need to carefully think about, and it really drives the first choice in algorithm about representation of our data, is about some fundamental thing called the curse of dimensionality in data. Now, this is the idea that 2 points in high dimensions are very far apart. And so, first of all, let me tell you what I mean by high dimensions. So, if we were doing that cat-dog classifying algorithm and I gave you the picture could be a 480 by 640 image. And so that's so if I multiply those two together, that's the number of pixels. And if it's stored in RGB, so red, green, blue format, a number for each, then actually a single image is defined by 921,600, apparently, numbers of parameters. This is a huge amount. And that's what we call the dimension of the input space. And we can generate all sorts of images in that space. Now, if we go back to a much simpler example where we have a one-dimensional input, so a single number, we can easily choose multiple data points that we evaluate on that to be close together. Now, if we extend this to 2 dimensions, to get the same filling, so if we fill a grid 3 by 3, we obviously then need 9 points with the same kind of spacing. Now, if you extend that up to 100 dimensions, to get the same amount of filling as our 1D example, what do we need? I did the calculation here. It's 5e to the 47. So an eye-watering amount of data. 100 dimensions is nowhere near 921,600 for just a picture input, right? The problem is, if you have very large input spaces, you require very large amounts of data so that you can generalize well. And really the central thing that I would say is that algorithms seek to do is to try and learn patterns in the input data so they can simplify the representation and understand the essence of the problem in terms of not just representing a picture of cats and dogs by just pure pixels, but understanding that there are features, representations in that data which are characteristic to understanding the difference between a cat and a dog. So a central idea is around the curse of dimensionality, that the data requirements explode in high dimensions, and therefore when we're picking our methods, we need to be really careful about not making that input dimension too large, or doing what we can to try and really isolate the minimum requirements in terms of the dimension of the input to build good algorithms. I think, so I mentioned the pink pants scenario, and I'll try and put it in a bit more context now. But one fundamental question on choosing your methods is, do the outputs matter? And so why do I say pink pants? So imagine there's a recommender system on Amazon, for example, and you interact with it, you have a purchasing history of buying purple pants, and then the recommender system recommends that it shows you adverts for me buying pink pants. If I don't choose to buy those pink pants, nothing really happens. Amazon don't do so well on their profits, but the decision is not critical. And then the algorithm can learn, it will show me something different next time. It might know that, okay, maybe I want green pants. And it can try that. But the outcome really doesn't matter. It's kind of, as long as it averages out. I would say that in many applications, particularly ones that digiLab focus in, are around safety critical applications, where the output really matters. Like if I'm going to give you a diagnosis based on some images of some x-rays, do you have cancer or do you not? I really want to make sure that I give you as accurate as possible information as possible, particularly protecting against false negatives in that example. Another application that we work on is in water treatment. If we get the algorithms wrong that don't control the water, then it has huge implications to the environment, to downstream water quality that we might use. It really matters. We need confidence in them. Another one in designing or controlling aircraft. If you're going to do that, then you need real reassurance about why those decisions were made. This kind of concept of explainability goes kind of in nature with the sort of measurements of uncertainty in deployment. So one thing is that these fundamental methods, ones that are equipped with uncertainty and ones that aren't equipped with uncertainty, are fundamental choices about how you set up the algorithm. And you need to consider, do your outputs really matter? So talking about the machine learning workflow, I think this is a nice image that tries to break down all the sort of tasks that you might do. And it's kind of classic LinkedIn clickbait. And some of them are informative. I've drawn a few at a time to try and give people an idea of how algorithms are constructed and the things to think about. And I think they're useful at that level. But what I would really guard against is the fact that every machine learning workflow just follows the same recipe. I think it's good to have general principles about how you construct these. I think I produce a similar picture when we talk about machine learning workflows later. But I iterate that you can break the rules. And depending on the task, you might have to do things differently. So I definitely think machine learning workflow understands some basic principles of what makes up a good algorithm around data preparation, about model selection, feature extraction, training, and then validation for sure. But I would say that, really be careful that don't think all algorithms fit into this kind of workflow. And then my last point really is around about how should you learn machine learning in this course or, into the wider sort of as you grow past this course and look at more complicated things as you start to do it in your job or in your studies. And this is not meant to be preachy, but this is just how I feel sometimes. I meet a lot of people which feel like the cat in the top right hand corner, and they know that data science is really interesting. They understand about big data needs. They understand that there is real value in their data, but they are a bit like a cat looking at a bowl of salad that is actually linear algebra. So it's a feeling that some of the maths gets in the way of them really understanding or deploying machine learning. And I would say you should avoid this kind of way of looking, that you should not take a bottom-up approach, that you have to understand the whole of maths to be able to be sort of worthy of doing machine learning. Is completely the wrong way of thinking about it. I think it's much better to dive in on problems and try and learn on the job, as it were. Try and pick a specific problem which is relevant to your interests, relevant to your job, and then try and do something simple in that space I would focus, and I think what this course tries to do is really focus on the understanding the big concepts of the approach before the details, and then you gradually pick the details up on the way. It's important that you know some of the details, but you can do it at the right level for whatever you're required to do. I think one thing people think is that machine learning is a theoretical subject, and yeah, under the hood it is maths and statistics and programming, for sure. But I would argue that it's very much a practical subject in the fact that it should act on real data. So this is why we coin this phrase AI in the wild. Data in the wild is real data. It's a practical subject. You have to prepare it. You have to understand it. You have to poke it. You have to try different things. And I think the only way you can do that is by learning by playing. So try and do the maths. Learn through trying. Try and program up little components of it so you can understand the key concepts. But it's not all essential. But I think in doing so, you pick it up much quicker. I think one of the scary things and one of the exciting things about machine learning is it doesn't stop. So the algorithms that underpin ChatGPT, I was hearing in research around 2019, so not that long ago, and now they've exploded into the sort of general use. But I would say that fundamentally under the hood, a lot of those principles are very common. Understanding the basics around. Later in this course, we're going to look at linear models, and you might say, well, linear models aren't as attractive as neural networks, but actually they completely underpin a lot of the machine learning things we do. So I think understanding these good, solid algorithms, things like random forests are brilliant algorithms for machine learning. They've been around for years, so it is moving fast. It's a really exciting topic, but there's some foundational stuff that will remain constant and useful for a long, long time. So don't worry about it moving fast. I think, let me underpin the results. Right, AI in the wild is about getting your hands on some real data or looking at real applications. So we're going to really try and focus on getting you through learning some algorithms, really focusing on general linear models, really having a good understanding of machine learning workflow. And at each step, we'll try and take you through the practical side of it. I would try and encourage you to follow those practical examples and then try one out on your own data set. There'll be a way of interacting with this course in terms of Discord. Like if you have any questions, you've tried it on your own data set, put any questions into that, and then we'll hopefully, the community or the team at digiLab Academy will help you generalize what you've learned in this course to start trying it on your own problems.